So, we are happy to continue our program with the talk of Professor Jonas Ilmavirta from Tampere University, Finland, and he will speak on spectral rigidity of planets.
Yeah, many thanks, Roman, for the introduction and especially the invitation. I hope you can see my slides and hear my voice well. So let me know if there's...
Yes, I see it well.
Excellent. So let me just also mention that if you have any questions during the talk, it's maybe easiest if you ask them in the chat. And if you have any questions after the talk, I'll be happy to kind of, I'll be able any interruptions, maybe more towards the end. And okay, so let's get started with the topic. So first I should mention that indeed I am at Tampere University now, but then next week I will be switching to University of Jyväskylä. So if anyone is wondering, I'm in the middle of changing affiliations. So this is joint work with Martin de Hoop from Rice and Vitali Kasnelson from New York. So I want to get started with this kind of a basic idea behind the proof or the method. So I'll put more content to it, but this is just a basic idea. So I'll start with the spectrum of frequencies. So I'll define what that is. And from those frequencies, I can compute something that I call the trace. So it is the trace of something very specific. And out of that trace, I will see where the singularities are. And those singularities will tell me something about what is called the length spectrum. And the length spectrum will then allow me to find a radial velocity profile. So this is the overall path I'm taking. So this is kind of my abstract, if you will. And then let me go and describe what the idea is. So introduce the concepts and tell how it's all supposed to work before going to the actual statements of the theorems and the data and such. Okay. So this is something to do with planets, as I mentioned in the title. So I want to discuss how these planets work. So imagine an earthquake, and the earthquake hits the Earth like a drum. So although the scale is very different and it kind of looks different, but the overall phenomenology is quite similar. So there is an event, and then that causes the thing to vibrate over time, and we can listen to the sound that it makes. So we can listen to the set of frequencies that are in this system. Okay, and there's these hits of a drum, these earthquakes happen over and over again. And these amplitudes of these various modes, so these overtones, if you want to call them that, they will depend on the event, but the actual set of frequencies do not, as long as we stay in relatively low amplitude so that we can still use this linear model. And this is an excellent model. And so if we don't really want to learn about these events, but we want to learn about the Earth, somehow the ambient space in which these events live, then we should not be interested in the amplitudes as much, and mostly in the frequencies. And in indeed, these frequencies are well known. So for the Earth, we can measure of the order of 10,000 frequencies. So of course, that is not the whole infinite set, but in practice, it never is. Okay, so there is this kind of data is something we can actually measure for our whole planet. Okay, so the set of these frequencies is what I call the spectrum of free oscillations. Okay, so they are oscillations and they are free because the boundary is not fixed. The surface of the Earth is free to move up, down, and sideways as it wants. So the boundary condition is of zero force and not of zero displacement. So that's why we are looking at kind of a Neumann kind of problem instead of a Dirichlet type problem. Okay, so these frequencies that we measure, they are actually the square roots of eigenvalues of an elliptic partial differential operator. So I call this the elastic Laplacian, and I'm not giving you the formula for this Laplace operator here, but it's close enough to the standard Laplacian just for the purpose of discussion. So this actual elastic Laplacian will have to operate on vector fields because the displacement is a vector quantity, so it has to somehow operate on that level. But these scalar models are perfectly fine for the purposes of this talk. So you can just think of a say a Riemannian manifold and the Laplace operator on it, or a Euclidean domain even, that is still a perfectly valid way to see all of this. Okay, so that is what the spectrum is. And then out of these eigenfrequencies, so this omega-1, omega-2, and so on, I want to construct what is called the trace. So now, out of these frequencies, the first one will be non-degenerate, so that is kind of the ground state, but then the other ones might have degeneracies. And indeed, if I have rotational symmetry, there will be a lot of degeneracies. So I'm not including multiplicity here, so that the same omega can appear several times. Okay, so if you want to solve the elastic wave equation, then you can do that using a Green's function. So it's a function of two spatial variables, x and y, and then a time t. Okay, and this g can be expressed in terms of these modes or eigenfunctions and the frequencies or eigenvalues, depending on what kind of a language you want to use. So you can express the Green's function in terms of these. But now the problem is that we know the eigenfunctions, the eigenfrequencies or the eigenvalues, but we do not know the modes. So if our data is only the frequency, we have no information on the modes, not even the boundary values. So if I take the trace, that will become independent of these eigenfunctions. So this is a nice thing to do at first. And I'm not taking the trace of the Green's function itself, but rather its time derivative. But that is only a minor detail. So I'm just integrating over this variable x, and I'm setting x and y equal. So that is the trace. And then it turns out that that is essentially the sum of all these sinusoidal functions. And now if you have a sum of these these functions, these smooth functions, it's an infinite sum. So you may ask, when is this smooth, or in what sense does it converge? And it does converge in the sense of distributions, and the limit is not smooth everywhere, but it is mostly smooth. So this function, so that this time t maps to this trace at the time t, has a singularity at capital T if and pretty much only if capital T is the length of a periodic ray path, or a periodic broken geodesic. So in that picture, I have a simple drawing. So that disk is kind of the planet. And then there is a periodic path which has these 4 legs. So it reflects 4 times on the surface and it repeats itself. So if the total travel time around that loop is a capital T, then there is a singularity in the trace. And if you noticed, I did not say that if and only if. I only said that if and pretty much only if, because there are some technical issues here, but those issues are not fortunately too big, and some of them can be assumed away. So just to be careful if there is something hidden there. So I will not go into the gory details here, but just to mention that there is something to be aware of. Okay, so this is the trace. Okay, so from these frequencies I got the trace, and from the trace I got the lengths of these periodic ray paths by looking at the singularities. Okay, and then we come to what I call the length spectrum. So the length spectrum is the set of all lengths of all periodic orbits. So I have a bad drawing here. So you notice that the ray can come, so it can be in the upper layer of the planets. So it can be in the mantle, it can reflect, or it can refract and go into the core, and it can do pretty much anything it wants. So that's a weird kind of ray, but the only condition I have for it is that all those individual things are admissible, so it's allowed to reflect just that way, and that the whole thing ends up being periodic. So that's the only thing I want, so there will be a whole lot of these things. So the length spectrum is the set of all these lengths or all these travel times. So to me, the travel time is the same thing as length. So from a geometrical point of view, I might confuse these two words pretty fluently here. So when I emit an interface, so a ray comes to an interface, it can choose to reflect or refract, and it can change polarization. So that is, it can kind of split 4 ways. And that can happen. So, and that is pretty kind of unfortunate, but also we have to be careful about how we define things. So we just allow our rays to choose any of these options. Okay, so this length spectrum is now computable from the eigenfrequencies, as I mentioned. So put those frequencies into this trace formula and then look at the singularities. But it can also be measured more directly. So there are ways to find the length of these periodic travel times in a system in principle by looking at the correlations in noise or some such thing. And if you want to do seismology on the planet Mars, as there now is a possibility, so we have had instruments there for a couple of years now, then both of these methods are in principle applicable there. Although on Mars the noise is a horrible problem, so it might not be practicable quite yet. Okay, so using this length spectral data is pretty much like travel time tomography, but without all the endpoints. So sorry, I'll check if there should be a drawing here. No? Okay. So if you're looking at this usual kind of travel time tomography, actually that picture will come a little later. Yeah, so you will look at the travel time between two points on the surface. So maybe there's an earthquake in Chile and you measure the arrival time in Paris. So that would give you some kind of information between 2 points on the boundary. But now I have no boundary in the sense that I have no endpoints. So everything I have is periodic. So of course the boundary is there and it does reflect stuff, but nothing ends there. Okay, so now this whole problem is difficult and it's non-linear, so it's natural to linearize it. So to study the linearized problem instead. And this is of course a very familiar instinct to many of us. So if I linearize normal travel time tomography, so like I mentioned before, so an earthquake somewhere and a measurement somewhere else, then if you linearize that, it leads you to geodesic X-ray tomography. So you know the integrals of a scalar field or a tensor field or some other kind of a geometric object over all these geodesics or other integral curves on your manifold. So this problem is relatively well understood on some manifolds. I can't say all manifolds, but still there is a huge number of examples, and so we can do a lot of things on simple manifolds, for example, and also on some non-simple ones. But what I'm looking at here is not this, but this periodic travel time tomography. And if I linearize that, it leads to periodic broken ray tomography. So now, so if I started in the Euclidean background, for example, then I might be looking at that kind of a pentagram I have there. So that is a broken geodesic, periodic broken geodesic that has 5 legs. So it can look like that, for example. And now I have the integrals over those. And I would like to determine a function from such integrals. And now this is only beginning to be understood on very few manifolds. So part of the problem is simply the question, how many of these periodic things are there? So if you make small variations, there is no guarantee that it will remain periodic, and indeed usually it will not. So how do you know that there are enough or densely many of these periodic broken rays? It is by no means clear. So even in the case of a closed manifold where you don't have any boundaries, but you still have this periodicity, it is still a non-trivial theorem that these things exist in sufficient numbers. So just asking the question itself is a little hard, and then of course answering the question will be even harder. So that restricts the kind of geometry that I can look at. Okay, so now these were just vague ideas, but the point is that all of this actually makes full mathematical sense. So if I have a spherically symmetric planet, and with radial velocity profiles, there could be one or could be several, and I can allow jump discontinuities, and with some mild geometric conditions, then that kind of a thing is determined by its spectrum or length spectrum. Okay, so this is a vague statement, not a theorem. I'll give a theorem in a bit, but just to give the flavor of what I'm going to achieve here. So roughly it means that Earth-like planets, like Earth or Mars or the Moon or some other things like that, they are locally uniquely determined by the spectrum of free oscillations. And locally means in the sense of a one-parameter family or in the sense of a differential, so a linearization. Okay, so this it's kind of the basic idea. And now I want to put some more precise meaning into all of this. So I want to discuss what spherical symmetry might mean and all these other mathematical assumptions that go into it, and then finally give the theorems and then give a few comments on the physics and one of the assumptions if I have the time. So if you look at the Riemannian manifold, so a Riemannian metric on the Euclidean unit ball, there are a couple of different ways you could see spherical symmetry. So a Riemannian metric does not correspond to any kind of elasticity. It only corresponds to, well, it can be isotropic, or then it can be very mildly anisotropic in what is called just elliptic anisotropy. So in that kind of a setting, there are two concepts of spherical symmetry that are kind of natural. One of them is rotation invariance, that if you take any rotation, capital R, of the underlying Euclidean space, then it pulls back the metric to itself. Or then you can say that it's radially conformally Euclidean, which means that the metric G I have is conformal to the Euclidean metric E, and the conformal factor is just a function of the radius, so the Euclidean norm X of X. Yeah. Okay, so these are two natural concepts of spherical symmetry. And now it turns out that these are equivalent. So up to changing coordinates, so not fully equivalent, but if you can make a rotation invariant change of coordinates, then these two things are exactly the same condition. So the point is that no matter how you think of spherical symmetry, it is very, very likely that we will agree on what we mean by that. Okay, so in spherical symmetry, things are easier because you can calculate things explicitly rather than just qualitatively. So to us, it's not quite enough to know just how things behave in principle, but we need to know some things rather specifically, and this spherical symmetry helps there a lot. So and one of the things where it helps is the geodesic flow. So it is very integrable. So there are a lot of conserved quantities for the geodesic flow, and that also helps with having a lot of these closed orbits, so these broken periodic rays. So the spherical symmetry makes all these things much more well behaved, and it's also a physically relevant scenario to be in. So the geometry behaves well if we assume the so-called Herklotz condition. And if I have the time towards the end, I have a section on this condition, but this is just what it is. So you can just think of it as this analytic condition that the radius divided by the wave speed has to have a positive derivative everywhere. Whatever that means geometrically, that's just a condition we can play with. And that turns out to be valid, for example, on our home planet of Earth. So it's not an outrageous assumption to make. Okay, and then there is the question of polarization. So we have in reality polarized waves. So for simplicity, I'm stating everything here for a scalar model. So you could have one or two radial wave speed profiles. So just the P wave and the S wave speeds. So that's kind of a simple formulation, but the results also hold for the isotropic elastic systems. So when you have two Lamé parameters and they are both fully radial, or maybe you should add the two Lamé parameters and the density. So things are a little trickier to state in that case, so I'm not going to give that in full detail, but just to mention that everything will work in that elastic case as well, so it does not have to be scalar. Okay, so the waves can split four ways at interfaces. So on the left, I have an incoming P wave, and it comes to this interface, which is horizontal here, and it can reflect. So it can reflect as a P wave or as an S wave, or it can go through, it can refract as a P wave or as an S wave. So it comes out four different ways. And if the material was anisotropic, this number 4 might be replaced by 20. So it can, there are cases where things are surprisingly complicated. So this number can go up very high. So isotropy makes life a little bit easier. Okay, so in this scalar case, the spectrum of free oscillations is modeled geometrically by the Neumann spectrum of a Laplace-Beltrami operator. So for a geometer or a PDE person, this is a relatively simple model, but of course you may or may not agree whether this counts as simple, but still this is simpler than the full elastic Laplacian thing. So this is just the scalar model. Okay, so I want to introduce the concept of a basic ray. So this is a subset of all the rays that I'm looking at. So I define a periodic program ray to be basic if a couple of conditions are satisfied. I want it to stay in a single layer. So it does not go through any of the interfaces. It stays in the mantle, or it stays in the upper core, outer core, or it stays in the inner core. It stays within one of these layers in your model. And it always stays in the same polarization as well. And it is of one of two types. It either reflects on one of the interfaces or it's totally radial. So here on the right, I have this blue planet with the surface and then two interfaces in between. And now I have two examples of a basic ray which stay within the middle layer. There is the red one, which keeps bouncing on the first or the uppermost interface. It keeps bouncing there, so that's fine. But it does not bounce on the other interface, so only bounces one. And then there is the black one that bounces between two interfaces, but it is radial. So it only goes toward kind of in the radial direction. So these are the basic rays. Okay, so these are much, much simpler than the full zoo of rays that I have available. Okay, so these constitute the basic length spectrum, and it turns out that this is enough to look at just these kinds of rays. These will determine everything. And one thing that causes trouble is conjugate points. So, so 2 points are conjugate if there are many almost equal rays, so broken rays or geodesics between them in a certain linearized sense. So if you're familiar with Riemannian geometry, then this might be a familiar concept, and if not, then this picture will be good enough. So if in some leading order sense that can happen, that 2 points are joined by many different rays, then you have conjugate points. So these points cause trouble in geometric proofs. I will not entertain you with the exact nature of the trouble, but just rest assured that there tends to be some. So we make two assumptions. So there are two kinds of conjugate points that cause us a lot of trouble. So one of the things that we assume is that there are only countably many conjugate points. So the countable conjugacy condition. So up to all these rotations and shifts you can make due to our symmetries. And the other one is the so-called periodic conjugacy condition. So no point should be conjugate to itself along a basic ray. So these are relatively mild conditions. I mean, of course, these are conditions. These are non-empty assumptions. But if you look at any of the physical models that are out there, they do satisfy these kinds of things. So these are not as outrageous as they might first seem. Okay, so before I state the theorems, I have to give a couple of the standing assumptions. So the profiles I have are radial and piecewise smooth. There are jump discontinuities, and there are proper jumps, so it's not just the derivative that jumps, but the actual function itself. The Herklotz condition is satisfied within each layer, so not maybe globally, but only within each layer. And the periodic and countable conjugacy conditions hold. And I assume that the basic length spectrum is simple, so that it has multiplicity 1, so that no length of a basic ray can appear in two geometrically different ways. So the spectrum is simple in that sense. And I also assume that the length spectrum is countable. And I will be using a parameter tau describing a family of models. So I have one parameter family of these models. So now this sounds like a long list of assumptions, but as I mentioned, in reality, so if you look at like the Earth models we have, these are actually satisfied. So of course it would be nice to get rid of these, but it's not entirely sure whether that is possible. Okay, so here's the first theorem. So if I have a family of nice radial velocity profiles, like I just described, so that all of these C tau profiles, so these wave speed functions, if all of them give rise to the same spectrum, then all of these functions are the same. So that is if I have a family of models that all give the same spectrum, then they have to be equal. And the variation of the same theorem, the same assumptions, but now instead of having the same spectrum, I have the same length spectrum, or just basic length spectrum, either way, and then it follows that they are all equal. Okay, so that's the main conclusion here. And so this spectral data, or this length spectral data, determines the interfaces and then also the radial velocities in some linearized sense. So we can locate where the interfaces are, and we can find the velocities between them. So there is an earlier result without all of these discontinuities, which is technically cleaner, but still a little bit of tedium there as well. Okay, so these are the main results. And now, just to close off, I'll not give you more of a proof than I had in the first section, just that was the overall idea, but I want to give a couple of comments on the physics of all this. So if you look at planetary models, then planets are almost symmetric. And that is just a fact of life, because the planets are relatively slowly rotating, and they are very, very massive, and that makes them very close to having spherical symmetry. Of course, they are not perfectly symmetric, and that is something natural to look into. Can you take perturbations of symmetric models, for example? But at least we are close to it, so it's not bad. And people in geophysics use symmetric models pretty often. And all the planetary models we know actually satisfy our assumptions. So most famously including this PREM, so the preliminary reference Earth model, which is kind of the standard model for the Earth, which is used for many practical applications. Okay, so of course we know that the Earth is not perfectly symmetric, but if you take the kind of the symmetric best fit model that we have, this PREM, then indeed our assumptions are satisfied. And then weirdly, this Herclot's condition seems to be satisfied in all of the models we have for the Earth and the Mars and whatever celestial bodies you might have. So you may ask, is it an assumption, or is it something that actually follows from physics somehow? We don't know. And then I should also discuss measurability, so whether things can actually be measured in practice. So the spectral data is measurable on the surface. So all these modes have non-zero surface amplitudes. So, but it can happen that I have a ray, so this red ray here is trapped by total internal reflection in the core. And then it seems that geometrically, the ray cannot make its way all the way to the boundary, but we can still somehow geometrically, through the trace formula, gain access to the red ray there. So that's a little weird. And you might expect that this at least has to be unstable if it's possible, and indeed it is. But it is possible. So the corresponding mode, if you look at it, so kind of an eigenfunction in some limiting sense, the amplitude plotted here will oscillate in the core, where it's a proper eigenfunction in the kind of more familiar look of it. But then when you go outside of the core, the amplitude will quickly die out exponentially, and there will be a very tiny little tail all the way to the surface. So if you take the high frequency limit, then the amplitudes will go down with increasing frequency, and also the relative amplitude at the surface will go down. So the amplitudes measured will be very, very tiny for these kinds of modes. And that means that if you have any noise, then that will be a problem. So that will cut off your data significantly. So as you would expect, if something is trapped in the core, then that is hard to see. And it's not entirely impossible, but just it will be hard. Okay, so now just to mention a few things about the Herclot's condition. So I don't have many minutes left, so I'll try to keep this quick and skip some of the things. So the classical Herclot's condition is just this. So my function rho is r divided by c, and the condition is that rho prime is positive, and that's it. But now I can look at the reduced phase space of things. So the space of all possible geodesics, so all possible positions and velocities, and that has dimension 5. So it's a three-dimensional planet, and at every point I have a two-dimensional sphere of directions. But now if you take out all the rotations in the system, you end up with dimension 2 only. So that means that a set of all rays that are truly different, they have dimension 1. So if you partition a two-dimensional thing into one-dimensional orbits, you end up with a one-dimensional set of rays. Okay, and the natural coordinates, you can choose the radius and the angular momentum L, and these make things rather convenient. And the properties these have are the following. Angular momentum is conserved. Also at interfaces, no matter what happens, it's always conserved. And this L stays below rho everywhere, and it can only be equal to rho if the radial component is 0 of the velocity vector. So that means that if I look at this plot of this rho function on the left, it means that my reduced phase space is just below the graph of that function rho. So my orbit, this blue orbit here, in the reduced phase space is the geodesic that is under here. So this turning point is this blob here on the curve. And you can have jumps in different directions, and those will be kind of represented nicely. And total internal reflection will be represented by a jump of this kind. So this green thing drawn here cannot make its way through because it cannot stay below the graph and stay with constant value of L. So that's kind of a quick drawing of what this Hercules condition means. So it just means that this function is increasing, and therefore that in a certain sense the reduced phase space is convex. So that's all the Hercules condition wants to say. But let me skip the details here and just mention, or just put everything together and just recall that the spectrum determines the length spectrum through a trace formula, and I can have jump discontinuities, and I can, using that length spectrum, I can find the velocity profiles, and all of this should be implementable, so there is nothing deeply non-constructive here. Okay, so that's all I wanted to say. Apologies for going 2 minutes over time, but thank you for your attention.
Thank you very much for your beautiful talk. Questions, remarks? And maybe the following question. Actually, this problem is known in geophysics for a long time, and there were some publications in this direction. Do you know some maybe old publication in this direction? Because the problem was very well known, and there is some literature, at least geophysical.
Yes, so you are completely right that this is a very old problem in geophysics because it's a very natural one. So, so of course, this is something that people would have solved numerically or by fitting parameters to data. So what we bring here is the ability to prove something, of course. So that is the novelty, I mean, not the problem itself. So yeah, unfortunately, I can't remember the geophysical literature as well. So, but if you look at these papers, so especially the one that I mentioned, which is on archive, that will have a geophysical review as well of these problems. So sorry if I can't answer more properly than that, but I'll have to guide you.
As I remember, there were some results of the following sense. If we consider, for example, acoustic equation with radial coefficient, when we can split variable x into polar spherical coordinates, and can consider eigenvalue together with the number L of angular momentum, and it seems there were some works when eigenvalues are given together with the number L of angular momentum, but I do not remember exactly. Really?
Yeah, so at least if you look at these these textbooks of geophysics, then this problem or kind of a version of this problem is often discussed. But what they often assume is that they have some kind of boundary data of the eigenfunctions. So if they know the boundary values of these eigenfunctions, then the problem becomes much easier.
Yes, of course, sure. Okay, but for example, in dimension 1, if we have, say, Schrödinger equation with symmetric potential, when
hello everyone.
When eigenvalues determine potential uniquely, and in multi-dimension, again we have a family of Sturm-Liouville equation depending on number L, angular momentum, and in principle one can expect that eigenvalues for two different values of angular momentum should determine a spherically symmetrical coefficient, something like this. But I did not think in this direction for a long time, and before I say something approximate.
Yeah, so it is indeed true that these different angular orders will somehow decouple and you have a family of these one-dimensional problems. So especially if you look at the linearized version of the problem. So it's been actually a common response to these kinds of problems we are doing, that people find this very natural, and they are often surprised to hear that this has not been done yet. So I mean, it's very natural to use these trace formulas or to study this problem, but it seems that the proof of this thing is still new, so that is kind of surprising. But I agree that many of the ideas were already there, so I'm not claiming that everything is perfectly new, just that we were able to finally put the square at the end.
More questions, remarks? If not, we have to start.
Роман Геннадьевич, можно поучаствовать? Роман Геннадьевич, можно поучаствовать?
Да, конечно.
So, may I ask the question?
Sure.
What is written here? Spectrum determines length spectrum through a trace formula. Is it a result or is it hypothesis? What is that?
Yes. So so that is a result. So I mean, you can. So as I mentioned, you can put this spectrum into the trace formula and then look at the singularities. So then, yes, it does determine the length. So it does determine the simple part of the length spectrum. So you need to have some kind of a non-degeneracy assumption. So if there is degeneracy in the length spectrum, then that might fall apart. But so there are some caveats. So it's not as strong as stated here, but indeed, so that is a theorem strong enough to prove our main theorem. Let me put it that way.
What does it mean? Through a trace formula. How? What is that?
Yeah. So let me give
how to determine length spectrum. How to extract the length spectrum from the trace of green function? How to do it? Is it possible in principle?
Yes, it is. So the thing you have, so you look at its trace function, and that function has some singularities, and you just look at where those singularities are, and that's all there is to it. And that you can do numerically as well. I mean, compute on 100 modes, and you can see effectively where the things are non-smooth.
But what about the length spectrum? Is it principle observable at the boundary from standard geophysical measurements, something like this? Is it possible to find it?
Yes, so it can also be measured more directly in geophysics. So, yeah, I think I mentioned it at some point.
I'm speaking about length spectrum, not omega, not frequencies, but length spectrum.
Yes. So the length spectrum. So this, so it can be measured two ways. So it can be measured more directly at the boundary, and it can also be found using those frequencies. So both ways are possible. And it's kind of good to have the same data accessible in two independent ways. So then you can trust your data much better.
And the last question. If you deal with the most general case, I mean, no assumptions about spherical symmetry or something like this,
Yes.
Are there any result which guarantees that the closed geodesic does exist? Do exist? Closed geodesics do exist.
Yeah, so I think that we can prove that maybe like one or two of them must exist, but what we essentially need is that they have to be dense for our tools to work. And that density is something we cannot prove. So that is completely unknown. And that's a problem even without boundary. So if you put a Riemannian metric on the unit sphere and ask how many closed geodesics are there, we'd think there should be infinitely many and they should be dense, but we just don't know.
So no strong mathematical results about existence of such geodesics in general case, yes?
Yes, exactly. So
okay,
no strong results.
Okay.
Yeah.
Do you know such a terminology? Whisper gallery, jumping ball, so on.
Oh yes, this whisper. Yes, these are kind of trajectories that are very close to the boundary, so bouncing off the surface.
It looks like this circle of questions also. Existence of whisper gallery, so on. So thank you very much.
Yeah. Thank you for the questions and comments.
And thank you very much once again for beautiful talk.
Thank you.
We will have now a talk of Professor Mikhail Isaev from Australia.
10 minutes. Excuse me, Roman Gennadievich, we have 10 minutes break. No. What is time for the next talk? Exact time. What is that?
Okay, exact time was several minutes ago, but we can make a short break.
Роман Геннадьевич, надо начинать. На самом деле 14:35, вот его доклад должен быть, Исаева.
Да, но по расписанию мы должны начинать.
Да.
I'll try to catch up and do a short version of my talk. See my face on a big screen. What we decided, should I start or?
Yes. It is better to start.
All right. Then, hello everyone. I'm calling you from Australia, and I would be very glad to be physically there, but unfortunately it's not possible. And today I'm going to talk about our joint work with Roman Gennadievich. And let me share the screen. Can you tell me if you are able to see my slides?
I see.
All right. So today I'm going to talk about a classical inverse problem of reconstruction potential from partial Fourier data. So this project initially was kind of designed for presenting some other results from nonlinear inverse problem, but then it turned out to be very fruitful by itself. And we already published 2 papers on this topic and recently submitted another one. So let me go straight to the problem. And somehow it's very basic. Even a student of second year or third year student will be able to understand that, at least in dimension 1. So we have some potential V, which is supported on a given compact set. And suppose we know its Fourier transform we had, but not everywhere, and possibly with some noise. So here, I'd like you to get used to the notations. So d is always going to be dimension. So BR is the ball of radius r, centered at the origin, and V hat, or sometimes when the expression is big, it's convenient to use the operator name F calligraphic, and it's a usual definition of the Fourier transform. So, and I don't know if you're able to see colors, but sometimes I put some words in blue, which means that there is a little bit more to say about that. So I mostly done it for my own purpose, just not to forget. So here, the ball of radius r, there are several ways how we can define balls. It could be a cube, it could be other norm, but we have results with all this variation. It's just for some methods, it's more convenient to work with cube. For some versions, it's more convenient to work with ball. All right. So now, let me tell a little bit of the background of this problem. So, yeah, I decided not to try to review all the literature because it's huge. You know that it's probably simplest inverse problem you can think of in terms of Fourier analysis. And Fourier transform was studied ages and centuries. But here, a few main topics where you can find this problem. So, for example, one of the hot topic is a synthesis of band-limited signal. So if you think a little bit about that, then it's exactly the same problem. It's just if we can reconstruct our function v, then if we compute another Fourier transform, we will be able to extend the data given for us from BR to a larger set. So also the same problem appears in the theory of super resolution. So we know that we have sometimes these blurry images that we want to make better. And these blurry images came from the fact that we know low part of the spectrum, but don't know the high part of the spectrum. So somehow, again, we get the same problem of recovering bigger elements or larger elements spectrums. And the third point is actually the way how we come to this problem. So we can treat this problem as a linearized version of some inverse scattering problem. So for example, scattering amplitude, for those who know what it is, can be approximated with Fourier transform. So and then the behaviors that we get here for this nice linear problem somehow describes or is a good presentation of what's happening in more complicated nonlinear problems. And we were able to establish similar results for nonlinear and linear case. But today we only focus on the problem one, which is stated above. By the way, right in the beginning of the talk, if you have any questions regarding notation, so I'm happy to, if you ask questions as we go. So let's talk about what the question we study. So we study the stability behavior in problem one. But before even talking about stability behavior, you may say immediately that we have uniqueness. So assume that two potentials, so the Fourier transform coincide on some ball, then they must be equal. So that's a classical exercise of the type that if your analytical function, and Fourier transform is analytical function because our functions are compactly supported. So if analytical function is zero at some ball, then it's zero everywhere. So we have uniqueness. However, stability is not that great. So in fact, the problem is exponentially imposed. That means that if you study, if you want to study stability estimate of this type, then we cannot hope to have something much better than some power of logarithm inside of here. And by the way, this notation of the norm, so here in the norm could be infinity or some Sobolev norm, so we have various results using various norms. And this R means that we consider restriction of these two potentials to the ball of size R. So that's exactly the data that's given for us. So there is a general methodic how to prove that this problem is exponentially imposed that goes back to Vitushkin and Kolmogorov and using notion of epsilon capacity and epsilon entropy. But since this problem is nice and linear, we'll be able to explicitly construct examples. And I'll talk about them later once we have our stability result on the screen. So the first idea that you can start of approaching the problem in hand is just to assign zeros outside of the given domain. So that's natural, and actually that was being used for many purposes and many people. And somehow it gives pretty decent result, especially if noise is, if the area that's given for us is big and the potential is smooth. That allows us to say that Fourier transform decrease sufficiently fast and that approximation with zero is reasonable. So, and today I'm going to talk about how we can enhance this approach, how we can do better, right? So, but before jumping into theoretical part and how we did it, I would like to show you some pictures. So we didn't do much of computations, but we did some, and I think it's good to show you them straight away so you can get an idea of what we get here. So the lines are pretty thin. Can you see them? Blue and red. Probably on the big screen it will be very hard to distinguish, but what's happening here is like we have this red thing that is a step function, so that's original potential, and we consider its Fourier transform, and we add a little bit of noise to that. And if we do just naive computation, that we get this green line here, so which completely miss this step. While with use of our methods, we were able to get slightly better, which is kind of captures this step in the middle. Of course, I'm showing you some pictures that like in the middle, so somehow if you make noise too big, then both methods are useless. And if your noise is very small and you have a lot of points, then both methods work. So if you have a large domain. So here it's like a boundary case where one method is stop working while another still works. And here we have a relatively small number of points. So additional noise is due to the fact that we don't compute integrals, we approximate it with the sums. And here another picture. So here we have slightly more complicated shape of the original signal. And the green is the naive approximation, and we see that blue looks much better. And at this point, I would like to say Roman's student Grigory for providing us with these pictures.
Grigory Sabinin.
Yeah, it's me. I'm very glad that you like these pictures. Thank you.
Grigory Sabinin is now in stage in Ecole Polytechnique, and we are
not a student. Sorry, it's an intern.
And we are preparing jointly with him, with Mikhail Isaev, a numerical paper which continues our theoretical studies with Mikhail.
All right. Do you remember the time we started? I want to time myself, but I forgot the time we started.
You start
Okay,
about at 41 minutes.
okay, that's all right. So I'm looking on the schedule. I'm supposed to finish in 15 minutes and a bit scared, but I'll try not to take much more than that. So now I would like to talk to you a little bit about theoretical results. And we had two approaches, and that resulted in several papers. So the first idea is kind of related to the argument of uniqueness that I already told you. So what we are going to do, we're going to try to continue to do analytic continuation. But of course, to continue it in the whole domain, it's not possible when you have the noise. However, what is possible is that we can try to extend the data from a sum ball to slightly larger ball, and then apply the inverse Fourier transform. So that corresponds to the naive reconstruction, but we do it not with the initial data, but first we extend or extrapolate the Fourier transform to slightly bigger ball, and then apply the inverse Fourier transform. So, and it turned out that we able to extend. Oh, not here. So we were able to extend our data into a ball, which is logarithmic of the noise times larger. So depending on the noise, if we can extend to bigger and bigger ball. And here you see this blue C. It's not the same as the C below. It's just all constants in this talk for the simplicity purposes will be denoted by the same letters T. And if you would like to see the dependencies and more accurate statement of results, I really suggest you to go and look at the paper, and I'll give you references later. So here the main point is that if you have moderate radius V, but which is could be quite a bit bigger than small r, depending on the noise, that we still have Hölder stability. So now that allows us to extend in a reasonable manner, and then we apply naive approximation of this extended data. And their approximation is something like r in power of minus m, where m corresponds to the smoothness. So that's a standard type of estimate of the decrease of the Fourier transform at infinity. So this, and we do the first step, continuation using the Chebyshev, the basis of Chebyshev polynomial. So basically we expand in Chebyshev polynomials and truncate at particular in some specific place that depends on the level of noise. So that's a result, one of our results. Here I tried to be a little bit more specific, so I put at least norms that we deal with. But again, the statement is not exactly the same as the statement in the paper, and I shortened it a little bit. But the main point is the following. So if you have a compactly supported potential V, and if we know that it is smooth enough, then if you continue in some way, so here I didn't specify how much I extend, but there is a particular radius we can extend and then apply inverse Fourier transform, such that difference is bounded in the following form. So we have a Hölder term, and we have a logarithmic term here. So, and of course, when delta goes to 0 and everything else is fixed, so it's correspond to the level of noise, then the logarithmic part dominates. But we found it convenient to have two terms because there is a additional error in power of minus mu in here. So for example, if R grows, then it allows sometimes that the first term is bigger. So basically, there is a little bit of trade-off. So we have that estimate is still logarithmic. So what I said before about exponential instability is true, but there is a coefficient that goes to 0 when R goes to infinity. So basically a larger domain of data, then exponential instability somehow disappears. So that's the result. And here parameter alpha depends on mu. So on this mu, when mu become closer to m, which is optimal in terms of the second term, then alpha become close to 0, which is not very optimal. But if if we decrease mu, then alpha could go up to 1, which so for example, alpha equal 1 correspond to naive reconstruction. And one more observation in the previous comparison with the previous slide. So here we just have one potential V, and that corresponds to the difference of V1 and V2. Okay, so we have that our problem is linear, reconstructions are linear. So basically we can study just the difference of the potentials instead of having them two. All right. So I hope I explained the result well enough. So now I would like to talk about its extensions. So in fact, in the same paper, we studied optimality of this parameter mu. And we proved that actually constructed explicit examples that show that it's not possible to get mu greater than m for dimension at least 2. So that means that this threshold m is optimal in dimension 2 and more, but for dimension 1 there is still a little bit of gap. So we know that this estimate is not possible for for mu greater than Gladk's smoothness plus 1/2, and we have this estimate for mu less than m. And also we also establish estimates for this reconstruction in Sobolev norms, and moreover we don't really need our potential V to be compactly supported. We just need it to be sufficiently decreasing. So that's in our second paper. And of course, depending on the rate of decrease, the parameter of exponent of this logarithm also changes. Depends on how fast we decrease to infinity. All right. So now I would like to switch to a second approach, which turned out to be also fruitful. And that's approach via parallel spherical wave functions. Closing bracket here. So the basis of spheroidal wave function was in fact discovered not that many years after Chebyshev, basis of Chebyshev polynomials, but then it was somehow forgotten, and only in works of Slepian it was rediscovered and reconsidered again. And after that, it turned out to be very useful in numerical applications, and it's quite a hot topic now. And people publish many papers on this topic. So, and it turned out that this wave function, parallel wave function, are useful for our problem as well. So let me explain first what they are. So we consider the following compact integral operator. So we, it looks like a Fourier transform, except we integrate not in the whole space, but from the -1 to 1. And here, for the moment, we consider dimension 1. All right, so this operator has eigenfunctions, and that's the eigenfunctions of this operator are called paralloidal spheroidal wave function. And it's known that they form an orthonormal basis in L2, and also it's known that corresponding eigenvalues are simples and non-zero. Thus, we can express the inverse operator in this using this series in terms of paralloidal spherical wave functions. So by the way, I hope I didn't say it, but I hope you can see that if somehow f is supported in the area such that this integral equal to the integral of the whole domain, then the what we're getting here correspond to equal to the Fourier transform. But inverse operator here deal with exactly the data that's given for us. So that's correspond to the restriction to a given set. So here it's -1 to 1, but it's possible to rescale it. So now, once we have this series, what we do is we truncate them. So we denote the sum of the first in terms as f and c -1, and p and c will be a projection. So, and then we are using the following lemma, which is true for any basis, and provided that we have some monotonicity of eigenvalues. So it's possible to estimate the difference between your function f and what I call here reconstructed value using these two bounds. So basically, what it means is that we can obtain the bound that we need using known estimates on eigenvalues of the operator, plus estimates on the approximation of functions with its projection. So, and then we digged out available literature, and using the best known estimates, we were able to get this result. So let me briefly explain what's going on. So here we deal with multi-dimension. So in order to allow multi-dimension, we need to consider functions along the directions, like so. We integrate over lines, and then for each of the line we solve one-dimensional problem using the lemma that I showed on the previous slide, and then from the integrals over corresponding to this one-dimensional problem, we use inverse Radon transform to reconstruct the potential. So briefly, could be written like that. And here, I put a formula that might look a little bit scary, but what we're doing here is we allow rescaling. So if we know, so in the problem statement, I remind you that R was a radius of given Fourier data, and sigma was a radius of compact support of potential. And then we need to take C, parameter C, to be equal R sigma. Then we will get that after corresponding scaling, we get that operator FC coincides with the Fourier transform. So then first, probably we can read it from bottom to the top. So first we construct these functions, then we apply it to a given direction. So we have this function for given direction theta, and then we apply inverse Radon transform to that. So the result that we get is the following. So it seems like we were able to achieve a similar estimate as with the previous approach, except because of the lack of results in the literature, we were able only to get a norm in minus d minus 1 over 2. But for dimension 1, it's a norm L2. And for some appropriate n. And the bound is some Hölder term plus some logarithmic term in power of mu. So, but of course, there is a room for improvement here. So we want to obtain any norm, but already a big advantage that here in this approach, we were able to deal with L2 noise, while in the previous approach, we needed infinity noise to be able to get required estimates in Chebyshev polynomials. All right, so I think that's it, and thank you very much for listening.
Thank you very much. Questions, remarks?
I have a questions. Did you try to, so you estimate your function from its Fourier transform restricted to a ball. Did you try to select the direction to consider some kind of cone in your ball, which means not all direction?
Yeah, I think it's plausible, and there are literature, especially people who are familiar with Radon transform. For example, you don't need two opposite directions, right? It's redundant. One is enough, but yeah, so we haven't tried that, but it's more like using known results from Radon transform that could be improved.
You have also result about stability of the unique continuation for analytic function. There's things like that also that can be applied in that direction, I think.
Wait a second. So if we consider analytic continuation, then I think it's still the same kind of problem. So you have exponential instability. Then I don't understand how a given direction could help with analytical continuation in particular direction. Can you explain more, please?
No, but I mean the fact that the estimate of your Fourier transform in some cone is upper bounded. No, I'm sorry. The estimate of your Fourier transform in a ball is upper bounded by some expression of your Fourier transform in some cone, provided that you have suitable assumption of this kind of cone or any subset of this ball. This is the result of stability of unique continuation that allows that, since you have something that is analytic in your Fourier transform. So if you're interested,
I see. Okay, I see. So that means that we can even precondition, so we don't need the whole ball in the beginning. We can
exactly. This is what I mean.
Let's start from cone and still have nice. Yeah, that's good observation. And I bet that we maybe don't even need the whole cone. Maybe. So, but yeah. So, but the problem turned out to be interesting by itself, even in this simple formulation, and we were very surprised that somehow was partially omitted in the construct of the parallel spherical wave function, while it's there naturally.
Okay, thank you.
More questions, remarks? If not, when Professor Laurent Bourgeois will continue chairing this session. Laurent, tu as oublié décalage d'horaire.
Oui, yes, exactly. I completely forgot. I suppose that there is a decay of 1 hour. Is it right?
1 hour,
Oui.
yeah. 1 hour in Moscow.
Yeah, I've completely forgotten this this detail. I'm very sorry.
C'est l'erreur, Laurent.
Yeah, we slightly delayed. Hello, Roland. Nice to see you. Long time.
Hello. I remember you, yes. So I guess there is 10 minutes of delay because you have waited for me, or?
Yeah, so not because of that. There was a delay before, but now we're 5 minutes over the schedule.
Okay. So if you like, I can continue to chair the session. It is up to you, as you want.
You should begin, Alexander Jollivet.
Okay. So now we're going to listen Alexandre Jollivet, who is both from CNRS and the University of Lille in France. And he will talk about analytic properties of a deformation path arising in the study of the Steklov spectral zeta function in a planar plane.
Okay.
So
do you hear me?
Yes.
Okay,
yes.
Good. So
and we see your slides.
Okay, thanks a lot. So first, I would like to thank the organizer for the opportunity to speak here. So I will talk about joint works with Vladimir Sharafutdinov and the results about analytic properties of this deformation path I will show you is rather a work in progress. So in itself, it's not so interesting, but the perspective might be. So we are not sure actually. So this will conclude my talk actually, this perspective. So let me remind the inverse spectral problem. So the inverse spectral problem is you consider a bounded, smooth, and simply connected planar domain omega. So, and you consider the Dirichlet two-Neumann operator of this domain. So it takes a smooth function at the boundary, and it gives you the outward normal derivative of the harmonic extension of the function f. You first take. So this is written here. So you start with f, you take the harmonic extension, and you take then the normal derivative. So maybe everybody here knows this operator very well. So I'm just recalling things. So it's a first order pseudo differential operator. It is non-negative and self-adjoint with respect to the L2 product, which is given here. So here, this sigma is just a normal measure, the canonical measure on the boundary of the domain. And the spectrum of this operator is just a sequence of non-negative numbers. So the first eigenvalue is 0. So this is the kernel of the kernel of the Dirichlet two-Neumann operator is made of constant functions. So 0 is a simple eigenvalue, and then you have the other eigenvalues which are counted with multiplicity and goes to infinity. So these Steklov eigenvalues are named after the Russian mathematician and physicist Steklov, who studied them in 92. So the direct problem is given the domain omega, compute the Steklov spectrum. So for the unit disk, it's just you can diagonal the Dirichlet two-Neumann operator of the disk. It is given by so here you have the eigenfunction, and the spectrum of the disk is just 0, counted one time, and all positive integers counted twice. So for the rest of the talk, I will introduce the notation lambda for lambda d. And the inverse problems we are interested in is given the Steklov spectrum, find the domain omega. So you have a natural gauge invariance for this problem. So this invariance has isometry of the plane, and the conjecture is as follows. So if you take two domain omega and omega prime, they will have the same spectrum if and only if there is an isometry between which send one domain to the other one. So I will not work with this formulation. I'm going to give you another formulation of this problem, a more general one. And so the formulation is now as follows. So you take a bioromorphism from the disk to the domain omega, and then using this bioromorphism, you can show that the Dirichlet-Neumann operator of the domain omega is conjugated to a very simple operator, which is just the composition of the multiplication operator by the positive and smooth function A times the Dirichlet-Neumann operator of the disk. So the function A is given by the bioromorphism by this formula. So this is the inverse of the modulus of the derivative of phi on the circle. And the perimeter of the domain omega is related to n-1 by this formula. The perimeter is just the integral of n-1 over the circle. So because they are conjugated, these two operators, they have the same spectrum, and so I will call the spectrum of this operator the Steklov spectrum of the positive smooth function A. And now the inverse spectral problem becomes, given the spectral Steklov spectrum of the function A, find A. Now the gauge invariance becomes the bioromorphism and bi-anti-holomorphism of the disk. So, and the conjecture is now stated as follows. So the spectrum, if you have two functions A and B, which are positive and smooth on the circle, they have the same spectrum if and only if you can find a bioromorphism phi or bi-anti-holomorphism phi so that this relation holds. So I will mainly work with the function A afterwards. But just before, I want to speak about classical properties of the Steklov eigenvalues. So the first classical property is the asymptotics of the eigenvalues. So you have a very simple asymptotics, which is as follows. So lambda k of omega is equal to, actually, this is lambda k of the disk of the same perimeter as omega, plus a remainder which decays as fast as any inverse power of k. So here it's the integer part of k plus 1 over 2, and I recall that this is the perimeter of the boundary, of the perimeter of the domain omega. And just to repeat myself, this quantity is just the Steklov eigenvalue of the disk. So you can find a proof of this formula in a work by Edward in 1993, but you have a previous reference to Melrose-Guillemin and Rosenblum. And so this asymptotics formulas has several generalizations. For example, here it will be in higher dimension. Here it will be for surfaces, Riemannian surfaces with genus and multiple boundary components. And here it will be a generalization for non-smooth domains. So, and of course you may also, so I do not pretend to be exhaustive for the references. You have plenty of works either in spectral geometry or in optimization. And so I just put some solid references. So, and another simple results about the Steklov eigenvalues is an isometric, an isoperimetric inequality. So the inequality is as follows. So it comes from a work by Van Stack in 1954. So the first non-zero eigenvalue of omega is less or equal to 2 pi over the perimeter of omega, with equality if and only if omega is a disk. So again, you have several generalizations of this formula. In this paper by Schiffer, it will be about product of Steklov eigenvalues of higher order. Here it will be for Riemannian surfaces with genus or more complicated, as well as here Jawar Polterovich. So in these papers deals with Riemannian surfaces with genus and multiple boundary components. And this work is about a multidimensional generalization of this estimate. So what the asymptotics tell us, it's already tell us that the asymptotics of the Steklov eigenvalue determines the perimeter of the domain. So it means that the perimeter of the domain is easily, it can be considered as a spectral invariant for our problem. So now I will introduce the main object we have studied these last years. So our object is a Steklov zeta function. So here, since the perimeter of the domain is known, I will fix it to 2 pi. So now this is our positive function, smooth function A will always satisfy this constraint. So the Steklov zeta function is defined as usual for complex number with real part bigger than 1. And so if you consider A equal to the constant function 1, then this constant function 1 is the A for the disk. So 1, when you look at the formulation of the Steklov problem with smooth positive function, 1 is related to the disk. So just consider here, you take 1, and the phi is just the identity, and you see that A equal to 1 is the disk. So because of this, and because of this asymptotics, where here you see actually the Steklov eigenvalues of order k for the disk, you obtain that zeta A minus zeta 1 is an entire function. So one of the first things we have done is to rewrite this entire function. For this, we introduce the Hilbert transform H, which is given by this. So H exponential of En theta, this is exponential En theta when n is bigger or equal to 0, and it is the opposite when n is negative. So this Hilbert transform has a very nice property. So the nice property is that the commutator of a smooth function A with H is a smoothing operator. So you have a smooth kernel, which is given by this. And so we will be able to rewrite this difference as traces, as a trace of a difference of powers of operators. So for this, I introduce new notation. So lambda A, which is just square root of m times lambda d composed with the multiplication operator by square root of A. So this operator lambda A is again conjugated to our previous operator A lambda D. So they have the same spectrum. So the spectrum of this operator lambda A is just, it's just the Steklov spectrum. And for another operator, I introduced dA, which is just square root of A times the derivative D, 1 over I derivative with respect to theta on the circle, and composed with the square root of A. So I consider the square root of this operator, and actually this operator, the spectrum of this absolute value of dA is exactly the Steklov spectrum of the disk, of the unit disk. So because of this nice property of this commutator, you obtain that lambda I square minus dA square is also a smoothing operator. And now if you look at the complex power of lambda A plus P0, so P0 is just the orthogonal projection onto the kernel of lambda A. So the kernel of lambda A and the kernel of dA are the same. They are actually spanned by the line. So the kernel is just the line spanned by 1 over square root of A. So the lambda A plus P, so the complex power of lambda A plus P0 is just given by this when you have diagonals, when you diagonalize the operator with an basis, an normal basis of eigenfunction. You do the same here. I record that that this operator of the same Steklov has the same spectrum as the Steklov spectrum of the disk. So you obtain this formula for this complex power of dA plus P0. And because of this property of smoothing operator of lambda I square minus dA square, you obtain that the complex power, so lambda A plus P0 up to the power Z minus this operator dA plus absolute value plus P0 up to the power Z is also a smoothing operator, and you can rewrite the difference zeta A minus zeta 1 as these traces. So now I will talk about our previous results with Vladimir. So one of the first results was
Alexander, excuse me,
yes.
What is P0? Could you repeat, please? P0
is just the orthogonal projection onto the kernel of lambda A.
On the kernel, it's just one-dimensional projection on constants.
Yeah, no, not constants. Here it's it's given by the function 1 over square root of A.
On what?
1 over square root of A.
Thank you, okay.
Okay? Okay, so one of the main results we have obtained this last year is a compactness criteria for smooth function on the circle. So for this, we have studied the Steklov zeta function at negative even integers. So if you take the traces, the previous formula with respect to the traces, the previous formula, you can rewrite these specific values as follows, as a trace of difference of operator. I remind you that minus 2k is a 0 of zeta 1. And so if you expand this trace in this basis, you have a very nice formula by Edward for the first zeta invariant, Z1. So you have this following formula. So here you almost see the Sobolev norm of A of order 3 over 2. What is missing is just the first, a control of the first terms A0 and A1. And for this, you can also show in the work by Edward that you can bound the uniform norm of log de A with respect to the mean value of A and zeta A minus 1. So it means that if you, so Z1 with zeta A minus 1 and this mean value of A control the Sobolev norm of A of order 3/2. And we can do actually, we can repeat the same reasoning using this estimate we have obtained here. And then you can show that actually this set, which is given, which is a set of smooth function, positive smooth function on the circle with the constraint of the perimeter, and with these bonds given by this, is actually a compact set in infinity of the circle. Okay. So the main idea here is really to see that this zeta invariant of order k gives you control of the higher Sobolev norm of A. So another result we have obtained with Vladimir is the non-negativity of the difference of zeta A minus zeta 1 on the real axis here. So you have this equality for any real S, and if you have equality here for a non-zero S, then A is conformally equivalent to 1. So meaning that the domain omega related to A is just the disk.
What does it mean? A is conformally equivalent to 1. What is that?
So conformally
A is a function, right? A is a positive
yes.
function.
So here B is conformally equivalent to A if you have such a relation. So it means that they are so they have the same Steklov spectrum, and this is the gauge invariance for the inverse spectral problem we are considering. Do you understand?
Okay, okay.
So
thank you. Please continue. Please continue.
Okay, let me repeat. So here you can find, for example, you have a domain omega, and this domain omega is related to a function A, as follows. Okay.
Yes, it's clear.
Then, if you consider this function B, it's like composing this phi with another phi1 here. You understand?
Okay, we introduce function B. What more?
So what I'm saying is that if you, for example, call this biolomorphism phi0 and call this one phi1, so A is related to omega by phi0, but B will be related to omega by the composition of phi0 and phi1.
Yes.
Okay. So this is what I call conformally equivalent. And so it means that if you look this at the level of planar domains, it means that they are isometric. So here, basically what I'm saying is that for non-zero real number, you have this inequality. And if you have equality, then the domain are isometric. Okay?
Okay.
Okay, so one identity. So this identity at zero is trivial. I mean, just for example, well, you have nothing to say about it. So if you have this inequality and this identity, then you recover a result by Edouard Wu in 1991, which was about the derivative of the difference at 0. So they obtained these results by a totally different technique. And here you see that this is just a straightforward consequence of our inequality. So now the proof of this theorem is based on a deformation argument, actually. So I will consider alpha, which is a smooth function in a real variable tau, and with value in the smooth function on the circle. And I will assume that alpha at time tau equal to 0 is equal to A. Alpha tau at any time tau is positive. You always have this perimeter constraint here. And I will also introduce a slightly different version of the Hilbert transform. It is the same Hilbert transform, except that h taken at the constant function 1 is equal to 0. So we were able to find a deformation alpha tau, which was equal to A at time tau equal to 0, so that the zeta function along the deformation is non-linguistic for any real S. So, and because alpha tau has also the very nice asymptotic behavior given by the point 2, alpha tau converges to 1 as tau goes to infinity, we were able to deduce the estimate which is given here. Because if you replace A by alpha tau, then this difference is decreasing to 0 as tau goes to infinity. And our deformation, alpha tau, satisfies actually an evolution PDE, which is given here. So d alpha tau over d tau equal to minus alpha tau lambda of alpha tau. So this is the function lambda of alpha tau plus the new Hilbert transform of alpha tau times the derivative of alpha tau. So my talk, the remaining minutes will be given to this, the analytic properties of this equation. So first, you can rewrite the right-hand side of this PDE as follows. So you can rewrite this as minus 4 times the real part of A plus lambda A plus bar, where A plus is somehow you are just considering the positive Fourier modes of A. And with this writing, you have already a very simple statement. So first, we will prove existence of for smooth initial data A. So this is a two-step proof. You start with A, which has only a finite number of non-zero Fourier modes. So A belongs to this finite dimensional space. So in that case, you see that this PDE becomes an ODE in this finite dimensional space. So you have existence of uniqueness of a smooth solution alpha tau for a small time. But because you know that the zeta function are decreasing, are non-ingressing into along this path, and because also you know that the average over the circle of alpha tau is also non-decreasing, because you just integrate over the circle this equation, and you have this positive number, then you obtain that alpha tau stay in a compact set of C infinity of S, which is given by this. And so you obtain global existence of alpha tau for initial data with only a finite number of Fourier modes. Now, for a smooth function, you approximate the smooth function A by function with belonging to Fn, where the big N will goes to infinity, and so that the approximation An satisfies these limits. So for each An, because of the first step, you have a unique solution alpha n, and because you have the decrease of the zeta function and the mean value, you actually have a uniform control of the sequence or alpha to n with respect to the Sobolev norm HK of on the circle. And if you put this uniform norm, you also into the evolution equation, you actually obtain by induction that you have also uniform control of the derivative with respect to tau of alpha tau n. So uniform over any time tau. And so from this, you extract a subsequence, and this subsequence will converge to the solution alpha of the theorem I showed you. Now, what is missing? So now we're missing some statements. For example, uniqueness. So here, actually, it is actually almost an elementary fact that you still have a uniqueness for this smooth positive function for any initial smooth positive function A. So it's some kind of Grunwald inequality, and you can also prove that if you have two deformation paths, alpha tau 1 and alpha tau 2, which coincide at a positive time tau, then they coincide at all times, for all times. But for these elementary statements, we actually have a proof which uses the next property. So actually, the path, deformation path alpha tau is highly smoothing. Because for any, if you start at time tau equal to 0 with a smooth function, at time positive tau, you have an analytic function alpha tau. So you obtain this exponential decay of the Fourier modes of alpha tau. We can also be more precise about the asymptotics as tau tends to infinity for alpha tau. I mean that we have a more precise statement than this one. So the more precise statement is that actually we have an exponential decay which is given by the exponents minus 2, 1 minus epsilon times the absolute value of the integer n for the nth Fourier coefficient of alpha tau. And this is epsilon here, it's just a small number between 0 1, and here the big O is independent of tau. So this gives you
Alexandre, I think it's
can I have 2 minutes?
Yeah.
Okay, so now I have we also have an analysis when A is not smooth. So when A is just L1 and A minus 1 is in LP for some P greater than 1. In that case, you approximate A by smooth function AN. You have, again, a unique solution alpha n. And this alpha n, you weakly converge to a weak solution alpha in L1. But again, because it is very smoothing, you actually have alpha is smooth, belong to this space. So it's smooth at positive time tau, and it is actually analytic at any positive time tau. And you have a control of the Sobolev norm of alpha tau. So it is uniform on any interval epsilon infinity where epsilon is the positive number. So it's controlled with respect to the LP norm of A1 and the L1 norm of A. So the consequences of these properties might be might be interesting, because if we understand the evolution of the Steklov spectrum along this deformation, it might suggest that we can reduce the inverse spectral problem to the question of local isospectrality in an analytic neighborhood of the unit circle. Okay, so I finished, and I'm sorry for the delay.
Thank you very much, Alexandre. Is there any question or comments?
Is it possible to use similar technique for some other inverse spectral problem? For example, we consider domain with Dirichlet boundary condition. Is it possible maybe to use something developed for the Steklov spectrum for other spectral problems?
But actually, this is so if you look at the equivalent for the Dirichlet problem, then you also have some flow like so here we have this deformation alpha 2, which satisfies an evolution PD, but you have some kind of equivalent deformation for the Dirichlet problem.
Very interesting.
But the real question is now is this point. So if we are able to understand this question, this evolution of the Steklov spectrum along this deformation, maybe we could do the same for the Dirichlet problem.
Very interesting.
But of course, I will not bet anything.
Okay.
By the way, it looks similar. It looks like something in the drum problem. I mean, the uniqueness of reconstruction. The uniqueness
but this is a question of Roman, I guess, no?
Sorry?
Yes. It was my question.
Sorry.
But for the drum problems, you know why I'm so positive? The reason is very simple. I can show you. So this is because this derivative with respect to 2. So the only if this term wasn't there, everything will work. So the only issue is to understand in another way this term here, because this here is just related to the Steklov eigenvalues. So, and this one is a perturbation, but this perturbation makes things, I mean, this perturbation is some kind of regularization. So it has to be here, but somehow if it wasn't there, everything would perfectly work. So, possible consequences would be consequences. But because of this bothering term, we have to understand things a little bit different.
Excuse me, can I add a couple of words?
Yeah, sure.
Roman Gennadievich asked about similar problems.
Yes.
Alexander, can you show the main equation? 5.
So here.
Yes, it is. Let me emphasize that it is a Riccati type equation. It contains quadratic terms on the right hand side, quadratically depending on the solution on alpha tau. And moreover, both terms are non-local. Such Riccati equation is very popular in geometry now. It is so-called Ricci flow. Ricci flow,
Okay.
it is also a parabolic equation with quadratical terms. Yes? And according to main ideas of Perelman, you know, quadratical terms are in some sense very bad non-linearity. Blow up is very typical for solutions of equations of Riccati type. And as Perelman, as far as I understand Perelman's main idea, curvature tensor can control the behavior of the Ricci flow. As far as curvature is bounded, so far the solution does not blow up. And some analogy is in our case. The control is done by the zeta function. As far as zeta function does not blow up, as far as the solution to this equation also is rather good. Okay?
Thank you very much. Thank you very much for very interesting comments.
Okay, thank you. So, is there still one question, maybe? If not, I suggest that we hear now Yavar Kian. Hello, Yavar.
Hi. So, okay, thank you for the invitation. Just a second. Okay, so thank you very much for the invitation. So I will it's quite a good point that you invited me to this talk, since my talk will combine two aspects of the title of this conference. That is both quasi-linear and inverse problem. So this work is based on joint work with Katalin Kartesa, Ali Faiz Mohammadi, Katja Krupschik, and Gunther Ruhlmann. So let me start with the general statement of this result. For this proposal, we fix omega to be an open-bounded set with smooth boundary of Rn and being bigger than 3. And we consider the following boundary value problem, which is an elliptic type of boundary value problem containing a conductivity, which has a dependency with respect to the space variable, but additionally dependency with respect to the solution and the gradient of the solution. So we have here a quasi-linear elliptic equations. And to this elliptic equation, you associate a Dirichlet boundary conditions corresponding to a constant function rho and some additional Dirichlet data that I will specify a little later. So here, of course, the dependency of gamma with respect to u and the gradient of u is nonlinear. So here we have an expressions or a conductivity which have nonlinear dependency with respect to the solution and the gradient of the solution. And our goal here will be to determine in some suitable sense the nonlinear conductivity or quasi-linear conductivity appearing in these equations from measurement of the current flux, which will be associated with the normal derivative of the solution of this boundary value problem weighted by the conductivity, associated with voltage applied at the boundary, voltage which will correspond to constant function plus some Dirichlet data. This will be the goal of our inverse problem. So now, let me say a few words about the motivations of this problem. So the first thing that I would like to say is that this problem can be seen as an extension to the nonlinear framework of the so-called Calderón problem. In the linear case, this Calderón problem goes back to the seminal work of Calderón of 1980. And the first positive answer given in the linear framework to this problem goes back to the 1987 and the work of Sylvester Ullmann. So here in the linear framework, you replace the nonlinear conductivity that I have introduced before by some expression depending only on the space variable. And to each voltage that you apply at the boundary, you associate the current flux. And this type of information gives you the Dirichlet-Neumann map. And the goal in the linear framework is to determine this conductivity from the knowledge of the associated Dirichlet-Neumann map. So here in our work, we want to extend this kind of result to the nonlinear framework and more general physical phenomena that not described by linear equation, but nonlinear equation. So here, of course, concerning the physical motivation of our problem, you have also the physical motivation of the usual Calderón problem, that is the connection with so-called electrical impedance tomography problem, and its application in geophysical prospection as well as medical imaging. In this context, the idea is to consider some more general model which cannot be associated with linear equation, but some more extended expression, conductivity, that depend also on the solution of the equation. So for the nonlinear expressions and our problem stated in this framework, we can mention several problems, several models, which are described by nonlinear elliptic equation, including model of the electrics, plastic modeling, electrorheological, and thermorheological, and several others. So here, our point is to consider some expression, nonlinear expression, nonlinear conductivity, combining three classes of dependency. So the first dependency is the dependency with respect to the space variable, with variation inside the open set. The second dependency is with respect to the solution. And the third dependency will be a dependency with respect to the gradient of the solution. We want to determine some class of conductivity, combining these three classes of dependency. So here the idea will be that in this class of conductivity, you will have conductivity admitting variation inside the system independently of the solution. That is what gives us the space dependency additionally to the dependency with respect to the solution of the equation. And the goal will be to apply our voltage and make measurement of the current flux on the accessible part, that is the boundary of the open set, in order to determine these properties which admit variation in the inaccessible part of the system corresponding to what happened inside the open sets. So besides this physical motivation, there's also mathematical motivations for the study of this kind of problem, coming first from the high nonlinearity and ill-posedness of this problem. But you can also see the mathematical interest in the study of this problem as the extension of what has been studied intensively in the linear framework, that is the determination of coefficient appearing in linear equation. Indeed, if you assume that here your conductivity has no dependency with respect to the solution and the gradient of the solution, you basically go back to the linear equation and the linear formulation of the Calderón problem. So this is somehow a natural extension of what has been intensively studied in terms of determination of coefficient for linear equation. So moreover, the class of conductivity that we want to determine, combining the free dependency, the space variable, the solution, and the gradient of the solution, correspond to an open problem whose study started in 1997 by Sun and Ullmann. Okay, so now let me specify a little more the position of the problem. Once again, I fix rho to be a real constant, and I consider again the following boundary value problem. And the idea will be first to say a few things about the forward problem. What will be the situation for the forward problem? So the first thing is to make some assumption related to the forward problem, which can be stated as follows. So we assume that our conductivity taken with respect to the variable associated with the solution at this constant rho, and with respect to the variable associated with the gradient of the solution taken at 0 to be strictly positive and smooth. In addition to that, we add some additional smoothness of these nonlinear expressions, which are given here in terms of its dependency with respect to this variable as a function taking values in C1 alpha with respect to the space variable. So assuming this kind of assumption, you can show that for
some Dirichlet boundary condition F sufficiently small, you have a solution of this boundary value problem. This is actually a simple application of the implicit function. This can be proved quite in a quite straightforward way without using strong properties of nonlinear elliptic equations. So you can prove that provided that this Dirichlet data F is sufficiently small, you have a solution of this boundary value problem. And after that, a sufficiently smooth solution actually. And after that, you can define the Dirichlet to Neumann map, which will send any Dirichlet boundary condition corresponding to the sum of a constant function rho plus some small Dirichlet data F. And to this type of data, you associate the normal derivative of the solution of this problem 3 weighted by the conductivity. And you get actually something which will enclose the data that we want to use in our inverse problems, that is the voltage applied at the boundary and the measurement of the current flux. And from this data, our goal will be to determine some general class of conductivity having this free class of dependency. So in all this talk, I will refer to rho as a variable for the solution of the equation and psi to be the variable associated with the gradient of the solution. So this is our goal. Now, before I start to state our results, let me say a few words about what is known so far for this class of inverse problems. I will try to review several results in that direction related to determination of nonlinear term for elliptic equation, mainly based on the idea that this class of inverse problems are not always well known. So the first thing that I would like to say is that you can divide this class of inverse problems into two categories. The first category, which is the historical one, corresponds to the idea that the behavior of your nonlinear term with respect to the solution is part of the unknown. So you have as unknown the dependency maybe with respect to the space variable, but also additionally some dependency with respect to the solution, which is part of the unknown. So this is the first class of inverse problem in that direction. The second class of inverse problem in that direction consider class of nonlinear term which have some specific behavior with respect to the solution. Namely, in that category, authors consider some polynomial type of behavior with respect to the solution of the nonlinear term, or holomorphic as an extension of this, but somehow it's comparable, holomorphic and polynomial. And the idea in this, of the result in the second category is to use the nonlinear interaction in order to improve results stated in the linear framework. So through this talk, I will focus my attention mainly on result in the first category. So my main interest here will be the result in this first category, where the behavior of the nonlinear term with respect to the solution of the equation is also part of the unknown. However, I would like to mention quickly that there has been an intensive study of inverse problems related to determination of nonlinear term in the second category. And in this second category, I would like to mention the work of Faiz Mohammadi Oksanen, Krupchik-Ullman, but also Lassas, Limatainen, Lin, and Salon. Okay, so let me start with the first result that I would like to mention. First result, which has been considered in the continuity of the linearization arguments introduced by Isaev in 1993. So for this first problem, we consider a semilinear elliptic equations with a semilinear term having dependency with respect to the space variable and with respect to the solution of the equation. And the goal of this problem is to determine this kind of general nonlinear term by means of the knowledge of the Dirichlet to Neumann map associated with this boundary value problem. And this result has been, this problem has been studied first by Isaev Sylvester in 1994 for the case of dimension higher than 3, and by Isaev Nachman in the case of dimension 2. I mentioned also in the case of dimension 2, the work of Emanuelov, Yamamoto, who have considered similar type of problem. So here the idea is that the authors prove that this Dirichlet to Neumann map determines completely this kind of semilinear term. However, the approach considered by these authors requires some strong assumption imposed to the class of the admissible semilinear term under consideration. Namely, they make some assumption that can be stated in its simplest form, that the semilinear term under consideration is Lipschitz with respect to the variable associated with the solution of the equation, which is rather strong assumption imposed to semilinear equation. So in the continuity of this work, there has been also results stated with partial knowledge of the Dirichlet-Neumann map, that is excitation and measurement applied to some portion, arbitrary portion of the boundary. So the voltage and the current are applied to an open set of the boundary of the open set. And here, in terms of result, I refer first to the work of Isaev of 2001. So in contrast to the previous result, this time Isaev considers a semi-linear term having only dependency with respect to the solution of the equation. So no dependency with respect to the space variable. I would like also to mention that in the same spirit, I have obtained quite recently a result, but for hyperbolic equations. The second result that I would like also to state in this class of inverse problem is a result due to Isaev of 2001, where Isaev treated the determination of a nonlinear semi-linear term having both dependency with respect to the solution and the gradient of the solution in the case of dimension n equal to 4. So in these two works, actually, Isaev treated simultaneously the case of elliptic and parabolic equations. Concerning quasilinear equations, which are the equations that we are interested in, I will mention several results, all of them stated for equations of this form. So we consider here the divergence of some expression capital J, depending on the space variable, the solution, and the gradient of the solution. So the first result that I will mention is considered in the case where the nonlinear or quasilinear expression that we want to consider or determine will be a conductivity depending on the space variable and on the solution. So this is a work of due to Sun of 1996, where Sun proved that the Dirichlet-Neumann map associated with this boundary value problem allows to determine this class of conductivity. In 1997, Sun and Ullmann extended this first work by showing this time that you can determine some more general second order nonlinear expression depending simultaneously on the space variable and on the solution by considering this time a matrix valued function. So they have shown the determination of this type of nonlinear term in some suitable sense. It's not full determination because there is invariance, of course. In the case of dimension n equal to 2, but also in higher dimension by making some analyticity assumption on the nonlinear term under consideration. I will mention also the work in the case of dimension n equal to 2 of Harvas and Sun, who have proved the determination of still a matrix valued function, depending this time on the space variable, but also on the gradient of the solution. So still in this idea of determination of quasi-linear term for elliptic equations, I mention also two works that has been devoted to the determination of conductivity having dependency on the solution and the gradient of the solution. So no dependency with respect to the space variable here. That is the work of Shankar and the work of Munoz and Ullmann. And finally, I will mention one joint work with Krupschik and Ullmann, where we have considered conductivity having space dependency, dependency with respect to the solution, dependency also with respect to the derivative of the solution, but only in one direction. The direction will be given by this omega, which is lying on the unit sphere. And here we have been able to prove that some partial knowledge, that is excitation and measurement located on some arbitrary portion of the boundary, allows to determine this type of conductivity, provided that you have some analyticity assumption imposed to this conductivity. Okay, so this is what has been proved so far for this class of inverse problem. And what I would like to say, and what goes back to earlier work, but mentioned in the article of Munoz and Ullmann of 2020, is that what has been open so far is the determination of a conductivity having this free class of dependency, that is the space variable, the solution, and the gradient of the solution in all directions. Since here we have treated the case of derivative in one direction. And this is actually what we want to consider here. And now I will go back to the statement of our problem. I recall quickly what I have already introduced before. That is, we consider the following boundary value problem with small Dirichlet data f and smooth Dirichlet data f. We associate with this boundary value problem the following Dirichlet-Neumann map, and our goal is to determine this class of quasi-linear conductivity from the knowledge of its associated Dirichlet-Neumann map along on this type of data, which correspond to the neighborhood of constant valued function. This is the idea in some sense. So the first result that I will mention will be stated with this rho, this constant rho, to be fixed at 0. So this rho will be fixed at 0. We are in the neighborhood of 0, and we have only access to the Dirichlet-Neumann map on the neighborhood of 0. That is only with small Dirichlet data. We consider for these two classes of nonlinear quasi-linear conductivity, to which we make some assumptions. So basically, these assumptions are related to the forward problem. We need to have assumption in order to be able to use sufficiently smooth solution of the forward problem. And after that, what we show is that provided that the two Dirichlet-Neumann map coincide on the neighborhood of 0, you can show that the two conductivity with the space variable admitting evolution in the open set omega have their derivative in the direction of the solution and the gradient of the solution that coincide at 0, all derivative. This is the idea. And the idea is that if you have this kind of result and you make some assumption of analyticity on the variable associated with the solution and the gradient of the solution, you get from this result the full recovery of your conductivity, nonlinear conductivity. This is our first result. For our second result, we will assume this time two classes of conductivity with some stronger assumption imposed to this conductivity. That is somehow some similar assumption to the previous case, but not just at 0. We do not consider it only for rho fixed at 0, but for all possible rho, which means that we have some stronger assumption imposed to the conductivity. And in addition to that, we add some analyticity of the conductivity with respect to the variable associated with the gradient of the solution. And provided that you have such assumption, what we prove is that if the Dirichlet-Neumann map for the two conductivity coincide on the neighborhood of constant function, then you can fully recover this class of quasi-linear conductivity. So here, of course, we do not have analyticity with respect to the variable associated with the solution of the equation, only analyticity with respect to the variable associated with the gradient of the solution. So these two works can be found in our article, which will appear soon in Advances in Math. Okay, so now let me make a few comments about this work. So the first thing that I would like to say is that in this talk, in this work, we give the first positive answer to the Calderón problem stated for this class of conductivity. As I said, having the three class of dependency, the space variable, the solution, and the gradient of the solution in all direction. And to prove this result, we make somehow assumption mainly related to the forward problem, to which we add some analyticity with respect at least to the gradient of the solution. As said in the work of, in the article of Munoz and Ullmann, this class of conductivity can be seen as some class of complete quasi-linear conductivities, combining what has been considered by Sun in 1996 and by Harvas and Sun in 2002. That is dependency with respect to the space variable and the solution in the work of Sun, and dependency with respect to the space variable and the gradient of the solution in the work of Harvas and Sun. So what I would like also to say, but I will recall a little later on in the basic idea of the proof of this result, is that our strategy is mainly based on this, is not mainly, but the starting point at least of this strategy is based on this idea of multiple linearization. Multiple linearization that have started with the approach introduced by Isaev. So Isaev considered the first linearization. Somehow the linearization can be seen as a derivation in some suitable sense. And Isaev considered only the first order derivation. The second linearization has been considered on its side by Sun and Ullmann in 1997. So which means that here they have considered the second order derivative in some sense. And the infinite order linearization have been introduced by Kurilev, Lassas, and Ullmann in a different context for nonlinear hyperbolic equations. So here actually we use it in a different way that has been used so far, which means that we use it in the idea of determining as much information as possible about the nonlinear term under consideration. In some sense, it is a natural vision of this class of problem, since here you have the first derivative and here you have the second derivative. our idea is to use all possible derivatives in order to get as much information as possible for this problem, which is an idea that you can also use for functions. First derivative, second derivative are not enough. You go on higher order derivation. So to give you an idea of the proof of this result, through this idea of multiple linearization, which in some sense can be seen as seeing all possible derivative of a formulation of our problem for the nonlinear equation, we manage in our first step to transform our inverse problem into some kind of linearized problem. So this linearized problem can be stated as follows. It is given in this proposition 1, which says that if you pick some function capital T, which will be continuous and taking values in a symmetric tensor of rank m, and you assume that you have the following identity. So this identity is considered for solution of this type of linear elliptic equations, and all possible solution of these linear elliptic equations, then you can recover your tensor valued function. So in our context, this tensor, which will correspond to derivative to any order of our nonlinear conductivity with respect to the variable associated with the gradient of the solution. This is how we make the connection between our linearization arguments and this linearized problem. And the idea for the resolution of this linearized problem is to combine several arguments, including first an argument of density of solution of this type of elliptic equation, to which you take the scalar product of the gradient weighted by the conductivity, and you take the density in the sense L2. To this, we add the use of some specific complex geometric optic solutions whose products will concentrate near lines that have some specific direction but goes through any point of our open set. This is the main idea, the basic idea that I will not go through due to the lack of time. And the construction of this complex geometric optic solution is inspired, has been considered in the spirit of what has been already considered by Greenleaf and Ullman in 2001. Okay, so now let me say a few words about a few prospects still in this direction of determination of nonlinear term. And the first prospect that I would like to talk about is an extension of the work of Isakov-Sylvester and Isakov-Nachman, a work that has been unchanged for 26 years. The idea here is to consider, again, this type of semilinear elliptic equations and to try to determine this semilinear term from the knowledge of the Dirichlet-Neumann map associated with this boundary value problem. So the idea will be to consider more general class of semilinear terms that in contrast to what has been considered so far by these two authors, that is, go further than limiting our result to semilinear term, which will be uniformly Lipschitz with respect to the variable associated with the solution of the equation. And this will give actually it would give a first improvement of this result, which, as I already told you, has been unchanged for something like 26 years. The second prospect will be related this time to the quasilinear parabolic equations. And the idea will be to consider this class of quasilinear parabolic equations, including a nonlinear conductivity, as well as a convection type of term, which will be also nonlinear. So this type of equations can be seen as a Fokker-Planck type of equations, nonlinear Fokker-Planck equations, but also nonlinear convection diffusion equations, and also generalized Viscosius-Burgers equations, some formulation of generalized Viscosius-Burgers equations. So it is related to several physical phenomena on which both the conductivity and this convection term have some important physical meaning. In this context, the idea will be to consider the following initial boundary value problem by fixing the initial condition at some constant values lambda and allowing some variation at the boundary of the open set given by this Dirichlet data. To this initial boundary value problem, we associate this map that sends any excitation applied at the boundary of the open set to the normal derivative of the solution of this initial boundary value problem weighted by the conductivity. And the goal of this problem will be to determine simultaneously these two classes of nonlinear expression by means of the knowledge of this class of excitation measurement map. And this in the first step for all possible values of constant lambda, and in the second step by fixing lambda at 0. This last prospect is a project which is in progress with Ali Faiz Mohammed. The study of this project is in progress with Ali Faiz Mohammed. Okay, thank you for your attention.
Thank you very much, Yava, for this nice talk. Is there any questions?
Maybe historical remarks. For example, in geophysics, the problem of finding conductivity from voltage to current map, from current to voltage map, was known many years before the work of Calderón. For example, in Soviet Union, there is known mathematician Tikhonov, and he is considered as one of the founder of this direction. For example, he proved already uniqueness for half space in 1949, for example. And so when in Russian Soviet Geophysical Institute, I am saying Calderón problem, they are strongly surprised. Say, why Calderón? And it is very difficult to explain. And for example, as about first uniqueness result for the case without spherical symmetry, without half space. For example, there was publication of Vladimir Druskin in 1980, the same year that Calderón paper. And for example, already in this year and independently of Calderón et al., proceeding from Tikhonov, he proved that piecewise constant conductivity is uniquely reconstructed from voltage to current map, current to voltage map.
But only in one-dimensional case, Roma, yes? In one-dimensional case, Tikhonov's result.
No, Tikhonov in one-dimensional case, but Vladimir Druskin in 1980 already in multi-dimensions for piecewise constant conductivity. And when, of course, there were very important publications of Kohn and Vagelius, who introduced the notion of Dirichlet to Neumann map. The point is, if we see the paper of Calderón, there is no Dirichlet to Neumann map in this paper. The Dirichlet to Neumann map was introduced by Kohn and Vagelius, some later publications. And so I suppose that these details are essential somehow. And for example, as about the origin of electrical impedance tomography in geophysics, I suggest to see in Wikipedia article electrical resistivity tomography, electrical resistivity tomography. You will see immediately photo of Tikhonov. You will see immediately some references. And as about the history of the problem, I suggest to see, for example, this article in Wikipedia with title Electrical Resistivity Tomography. I suggest to see publication of Vladimir Druskin, who was working in Institute of Physics of Earth at Moscow. And at present, he is working in USA in some geophysical company. And then Kohn Vagelius, who introduced for the first time the terminology Dirichlet to Neumann map in the context of electrical impedance tomography, because Gelfand used another terminology. He used terminology Wigner operator for the same map, but for the case of Helmholtz equation, Schrödinger equation, something like this.
Okay, thank you.
try to check that. But is it translated in English, this article you mentioned, or it is in Russian? Because I don't read Russian. Sorry for that.
I suppose that the article of Druskin is translated.
Okay, so if it's translated, I will check.
The article of Tikhonov, no, the article of Tikhonov is available, original article only in Russian, but when in Russia there were many publications who reproduced result of Tikhonov. For example, in Russian Mathematical Survey, to the jubilee of Tikhonov, there were publications who reproduced the result of Tikhonov.
Okay.
So,
thank you. I will try to add the Russian reference.
Is there any question?
Maybe
I have one about the numerics and the stability.
Okay, I am ready to cancel.
Do you know if for this kind of extended Calderón problem, I mean with dependency with respect to the solution and the gradient, do you know if there is some numerical work or some theoretical work but on the stability?
Maybe there is a work in that direction. I don't know the detail. No, I'm not sure they have done numerics. But actually, if you want numerics on that, you need to consider the simplest case, because in our case, it's uniqueness, and I don't believe in stability, because stability in this kind of multiple step ID, when you repeat this linearization, stability, if there is stability, it will be awful. So not in that case, but maybe in the case where the nonlinear conductivity depend only on the solution, it will be interesting to try some numerics on it. So this is.
I think in fact, I think that your assumption about the analyticity with respect to the third variable is something which will be difficult to treat from the point of view of stability.
Exactly.
I think it's okay for uniqueness, but to go forward and prove stability, this would be very. You should have a less an assumption with a weaker assumption to prove something for stability. I guess, but I don't know the problem. But
as I told you, maybe starting at least with a conductivity that depend only on the solution, not the space variable, not the gradient. This is what I was thinking about. In that sense, I'm not sure if there is, but it should be possible to do something in that direction. It should be possible. Even Isaev talked about this in the semilinear case, but I think that he was thinking about doing numerics if he hadn't done. But in that specific case where you have dependency only with respect to the solution, you can get stability, and I think you can go to the direction of numerics. This is what I believe, but you cannot do it in our context. This is too general. I think it will be complicated to have stability and this kind of things in this framework. But at least, as I said, as always, I see theoretical result. It always gives the directions. You consider the most general framework. And then if you want to do something more that is stability or numerics, you know at least that the uniqueness work in the more general framework. And you can start to study in the direction of this general framework. This is how, in my opinion, we should see this kind of results.
Excuse me, Mr. Chairman. Excuse me. I tried to ask the question, but you have broken me and ask yourself. So please be more attentive to the audience.
Oh, sorry.
Now, okay, but now there are
there was no.
Excuse me, but now there is no time for additional questions, and let us continue our session.
Yes. We are not in a hurry. In fact, you can ask your question. There's no problem.
Is there questions?
Please.
No more questions.
No more questions. Okay. Thank you.
So now we are listening Vladimir Sivkin from Ecole Polytechnique.
Yes. Hello.
Yeah.
can you see the screen?
Yes, it's okay.
Yes, we see.
We cannot hear you because you have to activate your microphone.
Ah, thank you. Okay,
yes, it's okay.
So it's okay. Dear organizers, thank you very much. I want to tell you about my work that was my work with Roman Novikov that was published this spring. So it is dedicated to phaseless inverse scattering with background information. So we consider Schrödinger equation and of the form minus delta psi plus v psi equal e psi, where E is the bounded potential with bounded support. For the Schrödinger equation, we consider the scattering eigenfunctions psi plus specified by the following asymptotics as x tends to infinity. Psi plus is the first term corresponding to the case when potential is equal to 0, plus the term corresponding to spherical waves, and here the function f is very interesting for us. It is called scattering amplitude, and all other small terms. Here, in order to study psi plus, and scattering amplitude f, we use Lippmann-Schwinger integral equation and formula that which links scattering amplitude with the potential v. Note that in the Lippmann-Schwinger integral equation, the integral kernel G plus is well known. For example, for dimension 3, it's quite a nice function, while for dimension 2, it's some special Ganka function. Recall that in quantum mechanics, the values of scattering function psi plus and scattering amplitude f have no direct physical sense, whereas the phaseless values of psi plus and scattering amplitude have probabilistic interpretation. That is why the subject of reconstruction of the potential V from phaseless scattered data has its interest. In this model there are a set of problems that can be posed. For example, the first problem is to find the potential V from the phaseless scattering amplitude F given for some set of pairs. And the first problem is the classical inverse scattering problem. If we reject the information about angles and consider the second problem, so we will have to find the potential using only the phaseless information of scattering amplitude, we will have a problem because for problem 2 there is no unique solution, while in while we want to see the model where there is a where one can reconstruct the potential from data in unique way. So in order to pose the problem, we add some additional information. We introduce additional scattering WGT such that the supports do not intersect with the support of potential V. And we consider the scattering amplitude for FG for the potential V plus WG. And so we pose the third problem. Problem is the following. We have to find the potential from phaseless scattering data F and also phaseless scattering data FGT on perturbed potential V plus WG, and we also take we also think that the scatters WG are given. So the problems 2 and 3 are the problems of inverse scattering without phase information. And Professor Novikov in 16 and with his PhD student Galtsov in 19 for uniqueness and efficiency of reconstruction showed that n equals 2 is necessary to reconstruct the potential V. In the present work, we show that the data for the reconstruction can be reduced considerably. But before then we go to the problem 3, we also have to introduce the problem 4, the problem on phaseless Fourier transform. So the problem here is to reconstruct function V from phaseless Fourier transforms of the following form and given backgrounds W1, Wm. So we start from the first problem. So we have the following theorem. Let functions V and W are integratable and their supports are localized in open convex bounded domains in space. And we denote by Fourier transform of function the following integral, and therefore the inverse Fourier transform have the following form. We also introduce the notation function chi of the set. It's a characteristic function of the set, and the difference of sets is a linear difference of such a way, not difference in the sense of theory of sets. And then we have the following results. Let the distance between supports of V and W is reasonable. Then only the data of W and phaseless Fourier transform of V plus W uniquely determine function V by the following 3 formulas. Indeed, if we consider them, then we hear that in formula 15 we see the inverse Fourier transform of the given function, and we had already talk about inverse Fourier transforms. Then we add to the to obtain u the convolution of given function with itself. We use a characteristic function, and the unique moment where it could be problems, it's a dividing of a function by the Fourier transform. But
excuse me, may I ask a question? What
Yes.
about W, function W? Is it known or unknown when we solve the inverse problem?
Yes, we think that W is known. W and this function are known, while V is unknown.
Uh-huh. Okay, thank you.
Okay. But in principle, under our assumptions on function W, the measure of the zeros of Fourier transform of W is 0 on the one point of view, and secondly, in principle, one can choose W's in such a way that there is no zeros of this.
But excuse me, to solve the problem, you need only one W in addition to the square of amplitude, right?
Yeah.
Exactly.
Only one function W.
Yes.
And
yes.
the only restriction is that W is positive, something like this. What is the condition?
No, the restriction considers the subsets of V and W. They should be the subsets of this function should be bounded, and we obtain the estimates for error for the case when V and W are also bounded.
But supports of V and W should be sufficiently disjoint as indicated in theorem 1. Distance between the supports should be greater than the diameter of a domain supporting unknown function V.
Yes, Roman, I am trying to recognize some kind of physical situation which correspond to this data. What is that? We measure the scattering data of the potential V plus W, right?
Yes, but so the physical situation is the following. We have some unknown object described by potential V, but we perform our scattering experiments in the presence of some additional well-known background scatterer prepared in advance. And this additional known background scatterer corresponds to function W. And so we need to do our scattering experiments and to measure absolute values of scattering data just in presence of some known scatterer.
But we don't know the scattering data of for W, something like this. No.
But
we assume it given. Yes. We know everything about W, right?
Yes, everything.
And the presence of this W helps to recover V, yes?
Yes, the presence of W helps drastically.
Fantastic.
Okay, sorry, Roma. May I remark again that it's nonlinear holography. holographic method.
Yes, of course, but for a moment, Vladimir presents linear situation because this result is of interest even in the framework of classical Fourier transform theory. So nonlinear will be several pages later. For a moment, everything in the frame of usual linear classical Fourier transform.
Okay, thanks. Very interesting. Let's continue.
You understand that the same idea as in holography, because in holography you have extra ray and you from record you have some film and you record the amplitude, but you can recover the phase.
Yes, of course.
Okay, can I continue?
Yes, continue.
Okay, thank you. And the questions, in principle, if the distance is less than diameter, but nevertheless greater than 0, then we have additional information about Fourier transform, phaseless Fourier transform of unknown function v. So the distance between the subplots is somewhat crucial. Okay, we continue. In order to go to inverse problem for Schrödinger equation, we recall that there is a Born-Faddeev formula that links Fourier transform of potential V and scattering amplitude for high energies. There is some another version for phaseless data that we used in order to obtain mathematical results. In principle, here you can see that using 25 in the results for the of the previous theorems, or one can obtain uniqueness theorem and reconstruction algorithm for inverse problem for Schrödinger equation. So let V and W1 satisfy the condition that I mentioned before, and the distance between the subplots of V and unknown potential V and known potential non-scatter W1 is greater than the diameter of the subplot of unknown potential, and we consider the case dimension at least 2, then the only phaseless scattering amplitude of perturbed potential and additional scatter uniquely determine the potential. So we stated the theorems of uniqueness, and then I want to show you the reconstruction algorithm that in principle based on theorem for Fourier transform with such some additional elements. Then we estimated, then we obtained error estimates for these formulas in terms of Fourier transform of potential f, because these formulas are made, in these formulas we reconstruct firstly the Fourier transform of the potential, and then we just take a inverse Fourier transform. So in this case, we obtained that the error also decays with growth of energy. The error is limited by L infinity norm of V and W, and here is there is also a problem which made by by division by Fourier transform of a scatterer. But in principle, the problem of choose a scatterer depends on experiment data, depends, but since W1 can be chosen, in principle, one can choose the function in such a manner to avoid the dividing by zeros. In principle, these estimates works for both cases when distance is sufficiently big or just more than zero. The only difference that is the exact formulas for these constants, but they looks almost the same. Okay, I have sometimes, so I want to show you the idea of proof of theorem 1. Here we use the following properties: the link of Fourier transform and convolution. We use that Fourier transform of the product is the convolution of Fourier transforms, and that the conjugated of Fourier transform is Fourier transform of conjugated function of minus argument. And in principle, that's all. So what we do? We write the following form. We take E as inverse Fourier transform of given data, and using the properties of modulus, we just open the brackets and obtain the sum of the 4 summands. And each of summands is the convolution that is each summand is an integral. And if we look carefully on every integral, we can obtain that such of them as a function of x has a bounded and bounded support, and using the properties, using the given conditions on the supports, we obtain that the supports of different integrals do not intersect. So that's a key idea. So we have that in fact E of x is sum of not 4 but 3 or even 2 integrals, and just multiplying this integral E by characteristic function of sets of supports of integrals, of corresponding integrals, we just obtain formulas like that. For example, the third integral is difference between I and I4 multiplied by characteristic function of the set. And then multiplying by taking Fourier transform of integral and using the properties of Fourier transform, we just obtain Fourier transform of potential as a division of Fourier transform of E3 by Fourier transform of W. So in principle, that's all that I.
But maybe let us return to the formulation of this theorem. And so actually presented proof is not so simple, but it is necessary to say that basic idea of this result goes back to some physical or even technical publication in Nature Communications for 2016. The precise reference is given in our article in Inverse Problems, and this formulation and this proof is a proper mathematical formalization of this idea, which appeared first in this article in Nature Communication for 2016.
Yeah, that's a work where there was a physical work, but there were no any mathematical
yes.
Consideration on the problem.
Yes.
Okay, this is the end, or?
Yes.
Just to understand, the distance between the d and omega is the Hausdorff distance?
Sorry, I don't understand your question.
What is the definition of distance between two sets?
Distance between two sets is just a supremum of sets between of distances between points of the of sets.
So it's not the Hausdorff distance.
Just metric distance.
Oh, okay, thank you. So thank you very much. Is there any questions, comments?
May I ask a question?
Sorry,
what happens if function w little by little tends to 0?
Yes, in principle, we consider the case that
what is wrong for reconstruction if w tends to 0?
Maybe I will explain it more quickly. And so, first of all, we suppose that w is compactly supported.
Okay, but nevertheless, if it is small enough, tends to 0, what is wrong for reconstruction?
But somehow w arises in denominator in formula C.
Okay, and no restriction of the sign of w, right? No restriction.
No. It may be complex, doesn't matter.
Even complex?
May be complex, this change nothing.
Okay, thank you. Very interesting.
Is there any other questions?
Oh, yeah, one question. Can W be just a constant?
No, because it has to have a compact sub.
Yeah, I know, but constant on the compact support.
Sure, it can
like
be.
Just an indicator of the set.
Sure.
Other questions?
So it would be a rather simple inverse problem if you just take W as a constant. Everything would be evaluated more easier, as I understand, right?
But not exactly, because in Formula 14 there arise Fourier transform of W in a denominator. And if we have characteristic function, for example, of some ball, then its Fourier transform has some zeros. So we need to do something in Formula 13 around zeros on numerical level.
But the set of zeros is rather poor.
Yes, but
yes,
nevertheless,
that's the point. Yeah.
Yes, Yes, of course, but numerically even this leads to additional work.
So we need to choose W such that there should be not much zeros.
It is possible to take compactly supported function positive which Fourier transform has no zeros. It is possible.
Oh, okay.
It is one possibility. But in principle, it is possible to do some additional work around zeros of Fourier transform FW. But numerically, it requires some additional work.
Okay, thanks for answering.
Thank you. Is there any other question? Did you try numerics?
So the situation is in inverse problems in 2019, there was our joint publication with Torsten Hochhage and Alexei Goltsov, where we did something but based on preliminary results, which are not so good when theorem 1. And it worked very well numerically. I invite everybody to see our article with Torsten Hochhage and Alexei Goltsov in inverse problems on Phaseless inverse scattering. It is in open access, but due to new theorem 1, everything will work much simpler and much more efficiently.
Roman, as far as I remember, in this talk, there was a number of W, no?
Yes, the point is that in our publication with Torsten Hochhage, Alexei Goltsov, as well as in my publication in Journal of Geometrical Analysis, we used two background scatterers, or three. Two. But from practical point of view, additional background scatterer requires to repeat experiments several times, and from practical point of view, it is much more convenient to have possibility to have just one.
Right. At last I remember your talk, yes, with the Goltsov.
And therefore, we are very glad that due to theorem 1, it is possible to simplify everything in several preceding works.
Yeah, very nice, yeah.
So, maybe one last question. One question. So, I guess it was the last talk. So I think, Roman, we can close this session.
Yes. Thank you very much for sharing.
Thanks to everybody.
Sorry for being late, but I will try to remember for tomorrow.
Demain, c'est ton exposé.
Yes, so it will be even more critical.
So thank you everybody for participation, and goodbye.
Okay, so see you tomorrow.
See you tomorrow.